everyone, thank you so much for clicking onto the video. Today we're going to be looking at understanding the term structural isomerism and determining the possible structural, displayed and skeletal formulae of organic molecules given its molecular formula. And then we're going to understand the term stereoisomerism as illustrated by EZ isomerism, including cis-trans isomerism where two of the substituent groups are the same. Now we're going to look at isomerism. So the definition of an isomer is a compound with the same molecular formula but with atoms arranged differently. So there are two types of isomer. The first is a structural isomer, and this is an isomer with the same molecular formula but a different structural formula. And the second is a stereoisomer, which is an isomer with the same structural formula but different spatial arrangements of atoms. So firstly, we're going to look at structural isomers. And there are actually three main types of structural isomer. And the first we're going to look at is a position isomer. And a position isomer is where the functional group is attached to the main chain at different points. So for this example, the functional group that we're using is this chlorine, because these are both haloalkanes. And so the left molecule is 1-chloropropane, because the chlorine is attached to the first carbon and there's 3 carbons in the longest chain, so it's a propane. However, in the second molecule, the chlorine is attached to the second carbon, and so this is 2-chloropropane. So these are both position isomers of each other because the chlorine is attached to different carbons in the chain, but they both make up this molecular formula. The second structural isomer is a functional group isomer, and this is when different functional groups are used to make up the molecular formula. And so if we have C2H6OH, we can form it in these two different ways. So the first is by using an alcohol. So this is ethanol. We don't need to put ethan-1-ol because the OH can only really be on one of the carbons, because if you wrote it the other way around, it would be exactly the same. And then the other molecule is what we call methoxymethane. And we'll look into these kinds of molecules a bit later on. And then the third and final type of structural isomer we have is a chain isomer. And this is when the hydrocarbon chain is arranged differently. And so, for example, for C4H9OH, we could have a straight chain alcohol. So this is butan-1-ol, because the OH is attached to the first carbon, and there's 4 carbons, so it's a bute. And then the other molecule, we have a branch. And so what we do is we name the longest chain. So the longest chain consists of 3 carbons. It consists of this one, and this one. And so, or you could have, it doesn't really matter which one the chain is, because if we had, for example, this carbon, and this carbon, but in a kind of L shape, that would also be the longest chain. So it doesn't really matter in this example. So we know that it's some kind of prop, and then this chain group here, and now we have to label them. So we have carbon number 1, carbon number 2, and carbon number 3, or we could have carbon number 1, carbon number 2, and carbon number 3. And now we have to think which one we use so that both the methyl and the OH have the smallest numbers possible. And so that means we have to use the bottom one, because the top ones, the numbers are higher. And so we get rid of those. And so we end up with the methyl we have to name first. So it becomes 2-methyl. And then because it's got 3 carbons in the main chain, we name it prop. And then we've got propan, and then the OH is on the first carbon, so it's propan-1-ol. Now we're going to look at stereoisomers. So in particular, we're going to be looking at EZ isomerism. And EZ isomerism is a form of stereoisomerism and occurs as a result of restricted rotation about the planar carbon-carbon double bond in alkenes. So here we have two stereoisomers. So the first, we have 1,2-dichloroethane. And so this is a Z because the Z stands for together. And so basically the things which aren't hydrogens, so these two chlorines here, they are together. So we call it Z12-dichloroethane. For the other stereoisomer, these chlorines are opposite each other. So we call it an E12-dichloroethane, the E representing opposite. So now we're going to look at some questions. For 1A, write the displayed and structural formulae for all the 5 isomers of hexane, C6H14. So the first one we can write will be the straight chain of just C6H14. So we would have 6 carbons in a straight chain, so that's 5 and 6, and then all the hydrogens attached. So this is the simplest one that we can think of. And then what we can do is we can start to add some methyl groups. So let's try and add one methyl group. So that would leave us with 5 carbons in the straight chain. So we'd have 5 carbons and a methyl group. So that is another thing we can do. And then we can then think, oh, I can put this methyl onto this central carbon, because if we put it onto this one, it would just be the same because it would be symmetrical to the one that we've drawn now, if we flipped it. And so we can't do that. So we can put a methyl onto the middle one though. So we can have a straight chain of 5 and the methyl group on the middle carbon instead now. So on the 3rd carbon. And then hydrogens everywhere else again. And so now we've finished looking at one methyl group. And because it's got 6 carbons altogether, we can actually fit another methyl group on. So we can probably have 2 methyl groups. And this means that we would have only 4 carbons in the main chain. So if we have 4 carbons in the main chain, how do we put 2 methyls onto this chain? Well, we can't put it onto the end 2 carbons because then we just extend the straight chain into one of the 3 molecules that we've drawn now. And so the 2 methyls must go on the 2 middle ones. So the first thing we can do is put a methyl on one each, and then hydrogens everywhere else. And then the other thing we can do is we can put 2 methyl groups onto one of the carbons. And so again, we have a straight chain of 4 carbons, and then say this one, we're going to put down 2 methyl groups, both onto this carbon. And these are all 5 of the isomers of hexane, because no matter how you twist them and rotate them, none of them will ever look the same as each other, but they all have the same molecular formula of C6H14. That's the definition of an isomer, is that they have the same molecular formula but different structural formulas. So now we're going to look at the structural formulas. So first, this one, we have a straight chain, which is just CH3, CH2, and for ease, I'm just going to put that in brackets and put down a 4, and then CH3. And then this bottom one, we have CH3, CH2, CH, and then we have branch chain and methyl chain, and then we have CH2 and CH3. And for the next one, I have CH3, CH3. That's supposed to have a hydrogen on it, actually. So we have CH, CH3, CH, CH3, and then a CH3 on the end. And looking at the top one now, I've got CH3, and then CH2, CH2, CH, and then a branched methyl, and then another CH3. And then finally, the last one, we have CH3, CH2, C, and then CH3 with a 2, and then CH3. So as you can see, all of their structural formulas are completely different, but they all end up with the same molecular formula, which is C6H14. And now we have to name these isomers. So the first one is easy because it's just hexane. There's nothing special about it, it's just a straight chain. And then looking at the one at the bottom left, we have this time only 5 carbons in the longest chain, and so it must be some kind of pentane. And then we look at the methyl group. So the methyl group will be on the 3rd carbon no matter what, because it's in the middle, and so we have 3-methyl pentane. And then going to the next molecule, this time the longest chain is 4, so we have some kind of butane, and we have methyl groups on the 2nd carbon and on the 3rd carbon, and so we have 2,3-dimethyl butane. And then for the one at the top, we have 5 carbons as the main chain, so it's some kind of pentane, and we have 1 methyl group. And there are 2 ways we can label the carbons. We can label them 1, 2, 3, 4, and 5, or the other way around. And the methyl group is either on carbon 4 or carbon 2, so it has to take the lowest value, so we need to get rid of the numbers on the top. And so the name of this molecule is 2-methyl pentane. And then for the last one, the longest chain is 4 again, so we have some kind of butane, and we have 2 methyl groups, and they're either on carbon 3 or on carbon 2. And again, we have to take the lowest number, so we get rid of the numbers on the top. And so the name of this molecule would be 2,2-dimethyl butane. You have to remember that if we have 2 methyls, so 2 methyls on the same carbon, you have to state the number twice, 1 for each of the methyls. So before I move on to the second question, feel free to click off the video and try it for yourself first. So there are 6 isomers of the alkenes with molecular formula C5H10, and the displayed formulae of 2 of these isomers are given. Draw the displayed formulae of the other 4 isomers and name all 6 molecules. So first, let's just start off by naming these 2. So first we identify the longest carbon chain. So the longest carbon chain for this would be 4. So we can name them, label them, so we can't have the numbers at the top. And so it must be some kind of but-1-ene because we have 4 carbons in the longest chain. And because the methyl is on the 2nd carbon, we call this 2-methyl but-1-ene. And then for this second one, we have the longest chain, which is 5. So we can label them 1, 2, 3, 4, and 5, or the other way around. And so this becomes pent-1-ene because we've got 5 carbons in the longest chain and we don't have any branches. So it's just a simple pent-1-ene. So now we have to think of the other isomers of these two molecules. So the first thing we can do is we can write down a molecule where we move the double bond. So if we take pent-1-ene and we move the double bond to between 2 and 3, we can get another isomer like that. So we have, and then we're going to put the double bond in. So we have a carbon with another hydrogen, and then another carbon with 3 hydrogens. So this could be an isomer, and this is pent-2-ene. But now we have to remember that pent-2-ene can actually be written two ways, and so there are actually two isomers of pent-2-ene. We have the E and the Z. And so we get, if I just zoom in on the double bond, we could have a hydrogen, and then we have C2H5. Then here we could have CH3, and we see that when we divide it horizontally, the two substituent groups which aren't hydrogens are on opposite sides on the first one. So this must be the E pent-2-ene. Whereas on the second one, on the bottom one, they're on the same side, and so we call this Z pent-2-ene. So now we've managed to get two isomers. There's still two more. So now we've moved the double bond, maybe we could try moving the methyl. So if we use isomer 1 and move the methyl to the third carbon, that forms another isomer. So we have CH3. And because the question says write the displayed formulae, you should probably write out, instead of writing, for example, C2H5, you should probably write out all the bonds. But I'm just doing this to be quicker. So we have CH3 and then CH, and then I'm going to put a methyl group here. And then we're going to have a carbon, and this is going to have two hydrogens now. And then we're going, and then we're going to have a carbon with only one hydrogen, because then we're going to have a double bond and then a carbon with two hydrogens. So this is another isomer. And so we have 4 carbons in the longest chain, and this time the methyl group is on the third carbon, and so this is 3-methyl but-1-ene. And then there should be one more, and this last one is probably the hardest to come up with, but it's when we move the double bond and also the methyl group. So we could have CH3, carbon, and then a CH3. And so we call this 2-methyl but-2-ene, because if we label the carbons, we have 1, 2, 3, 4, or 1, 2, 3, 4. So no matter which way we do it, the double bond will always be on the 2, because we have to pick between 2 and 3, and 2 is the lowest number, and so we'd always pick 2. And so this methyl group is also on this second carbon, and so this is 2-methyl but-2-ene. And these are all 6 isomers of C5H10.